Hello again. Welcome to Dawood Academy. In this video, I'll be going over how to calculate the estimate of the instantaneous rate of change using the centered interval method. In the previous video, I covered how to calculate an estimate to the instantaneous rate of change using the preceding following method. We also covered in previous videos how to calculate again the estimate of the instantaneous rate of change graphically from a well graphed equation or function, and that method works very well when it's on a grid paper or graphing paper. But in this method, we're still going to be going over how to find an estimate, so it's pretty accurate but not exact. So it's not an exact value, it's an estimate of the instantaneous rate of change. And we'll be using today the centered interval method. So in the centered interval method, what we will be doing is we're going to be first graphing the function, and then from there we choose a point of interest where we want to find the instantaneous rate of change at that value. So we first start off, let's defining a function. So let's define a function f of x equals x squared, a very simple quadratic function, and we'll sketch this function. So you can use a table of values, or you can use the 1, 3, 5 step pattern when you're graphing a quadratic. In the 1, 3, 5 step pattern, as long as the leading coefficient is, in this case, is a 1, right? There's nothing there, that means there's a 1. So it follows a 1, 3, 5 pattern where starting from the vertex of the quadratic function or the parabola, starting from the vertex, you would move 1 unit to the right and you would go up by 1 unit. So our first point moving to the right would be from, and we know that the vertex is at 0, 0. Okay, so if you want to use a table of values, you can, but if you know that the vertex for this type of function is at 0, 0, so that's your first point. From the vertex, you would move 1 unit to the right, and then you would go up by 1. So the first coordinate to the right of the vertex would be at 1, 1. And since the parabola, in this case, the parabola is reflecting across the y-axis, so if you move 1 to the right, you can also move 1 to the left, and you go up by 1. So we move 1 to the left as well, and we go up by 1. So that point here would be negative 1, 1. From either side, we can start again from the point that we have on the right, 1, 1. We move 1 to the right again, so to 2, x equals 2, and we go up by 3. So that would land us at here, right? So if we start at, if we move 1 to the right, we go up by 3. 1, 2, 3. That would land us here at 2, 4. And then to the left, again, from the second point that we have, the left of the vertex is at negative 1, 1. From there, we move 1 to the left. So 1 unit to the left and up by 3. That would land us at negative 2, 4. Now, we can trace the quadratic. And as you see, let me just get you a better sketch. This is a sketch, it's not a perfect graph. If you want to have a better, a more accurate, but not exact function, you would use graphing paper, or you'd have like a better sketch. It's harder on the computer, right? So with the mouse, but to get like a more symmetrical graph of the parabola. But in this case, we have the functions graphed for us, and we want to find the instantaneous rate of change at x equals to let's find it when x equals to 1.5. So at 1.5, what I'm going to do is I'm going to change the color to like a pink here, and I'm going to extend at 1.5, so approximately here. We're going to extend to the function. And I'm going to draw a dot here. And then from the dot, I'm going to extend a line. Again, we can change the color to an orange. And this line passes through only one point on the curve. And that one point is at 1.5. So I'm going to try to get that there. There. So we have now the function passing through one point, and it's x equals 1.5. That's the slope of the tangent. We know the slope of the tangent gives us the, in this case, is a very good estimate of the instantaneous rate of change, or how y is changing with respect to x. Now, with the centered interval method, what we're going to be doing is we're going to find 2 points, because we know that we can't find the slope of a line that passes through one point using a mathematical approach, because you only have 1 point on the function, right? We only have 1 point on the graph. So what we're going to do is we're going to have that single point centered between two very closely associated points. And from there, we would use that as our instantaneous rate of change, or that value that we get between those two closely associated points. Because they're very close to the point of interest, they would be representative of a good estimate of the instantaneous rate of change. So I'll show you exactly what I mean. In this case, we have x equals 1.5. So the point that we have is x equals 1.5. So this is the point that we want to find IRC at x equals 1.5. So what I'm going to do is I'm going to take the 1.5 and I'm going to find a value to the right of 1.5, very close to it. I can get as close as I want. I can choose, like, for example, 1.6. And I'm going to choose another value to the left of 1.5. And it's going to be from this, it's going to be decreased by the same increment that I increased to the right. So I increased to the right from 1.5 to 1.6 is a 0.1. And then from 1.5 to the left, I want to go to 1.5 minus 0.1, which would give me 1.4. So those are my two x values that I'm going to choose that are closely associated to the point of interest on the curve that I want to find the IRC, or the instantaneous rate of change. But now I have 2 points, so I can easily find the slope across 2 points. What I would need is the x value, which I have. So I'll call this x1 is 1.4, and x2 is 1.6, and I need to find the y1 and y2. So y1 is basically f of 1.4. So 1.4 as is your input value into the function, which we know is f of x equals x squared. And then y2 is f of 1.6. Okay, so now I have the data. What I need to find is the estimate of the instantaneous rate of change. So I can just write IRC estimate, EST, is basically the slope of the secant crossing those 2 points, x equals 1.4 and x2 equals 1.6. So from here, I follow the formula y2 minus y1 over x2 minus x1. So at y2 is f of 1.6 minus f of 1.4 all over 1.6 minus 1.4. And then what I'm going to do next is I'm going to calculate the difference between f of 1.6 and f of 1.4. So f of 1.6, and my function is f of x equals x squared. So I'll put that into the function, 1.6 squared minus, and then f of 1.4 is 1.4 squared, divided by the difference between 1.6 and 1.4 is 0.2. And then all I need to do now is input that in the calculator. So 1.6 squared is 2.56, and 1.4 squared, let's get that value, 1.4 squared is 1.96. 1.96 all over 0.2, and then I just have to input this in the calculator again. Divided by 0.2. And this gives me approximately 3, positive 3. So we can check this value, but a good estimate of the instantaneous rate of change using the centered interval method is 3 for when x equals 1.5. Again, this is an approximate value. It's pretty close to the answer, but it's not an exact value. In our next video, I will be going over the difference quotient. And the difference quotient is, again, an algebraic process. Is some derivation involved and formulation. But from there, we can actually get the exact value for the instantaneous rate of change. And this is very, very important for, as I mentioned, in many application style type of questions. And yeah, so we can use that in 2 ways. We can actually get the exact value, or we can get an equation of the instantaneous rate of change. With the equation, we can find the slope of the tangent or the rate of change, instantaneous rate of change, across any point on the function. So we will see that later on in the difference quotient in another video. So thanks a lot, guys, for coming to this channel and for supporting this channel. We will be posting more and more videos in the near future of the content, math, sciences, microbiology, biology, physics, chemistry, and I'll be going over more and more calculus material. So this is more of a series of pre-calculus content before I get into the derivatives and using derivatives to calculate the derivation of different functions and different equations, and using that to find the rates of change, to be able to graph complex functions, as well to solve word problems involving rates of change type of questions with volume, with profit functions. So thank you again for watching this video. If you like this channel, please subscribe, click on the like button, share with your friends, and thanks a lot, and hopefully in the near future you'll enjoy more and more videos from our channel. Take care and good luck.